On the morning of December 1st, astronomers reviewing overnight data expected to see the usual outbound glow of 3i Atlas as it moved deeper into the inner solar system. Instead, something else appeared in the telemetry. Not one object, not two, but several new bodies, each faint, cold, and entirely unannounced, entering the same observational corridor that 3i Atlas passed through only days earlier. The signals were subtle at first, small dips in a background starlight that hinted at movement. When cross-checks came in, the pattern became undeniable. Multiple new objects had entered view, each following a trajectory that traced uncomfortably close to Earth's orbital path. These were not random rocks. Their light curves were smooth, their motion was coherent, and their spectral signatures suggested something astronomers rarely see from distant objects in early detection windows. Organized activation, the same quiet behavior that made 3i Atlas so difficult to classify, is now showing up in more than one object. This is no longer a story about a single interstellar visitor. It is the beginning of something broader, a pattern that is only now taking shape. Tonight, we examine the data, the trajectories, and the physics behind these new arrivals, and we ask a question that has been whispered across observatories all morning. What if 3i Atlas was only the first step in a larger wave entering our solar system? Let's begin. The first signs did not arrive with a flash, a spike, or anything dramatic. They came quietly, almost politely, tucked inside the early morning observational logs from December 3rd. Two observatories, one in Chile and one in South Africa, were running routine sky sweeps as part of their nightly tracking of 3i Atlas's outbound trajectory. These sweeps are usually uneventful. Most nights, the raw data is a long scroll of background noise, cosmic rays, faint stars, and predictable motion from catalogued objects. But at 0412 UTC, both observatories registered something that didn't match any known signature. It was not a brightening, it was a dimming. A thin, precise reduction in starlight intensity lasting less than a second. At first glance, it looked like an error, maybe thin cloud cover drifting across the lens or a calibration shift. These are common explanations that analysts check before investigating deeper, but the weather logs were clear, and the calibration systems had not adjusted. When the teams overlaid the data, the timing matched exactly. Both observatories recorded the same dip at the same universal moment with the same shape. This alone was unusual, but anomalies happen, and one coincidence is not enough to convince anyone. What triggered the first wave of attention was what came next. As the Chilean observatory reviewed the preceding 10 minutes of raw data, it found 3 more dips, weak but consistent, each separated by near-regular intervals. When the South African team checked their archives, they found 2. All 5 events shared the same structure, same depth, same duration, same slope on the entry and exit. A dimming event this clean points to one thing, an object crossing in front of a distant star. This is called a stellar occultation, and it's one of the most reliable ways to confirm the presence of faint objects long before they become bright enough to be seen directly. Large bodies, asteroids, comets, dwarf planets, sometimes betray their presence by briefly blocking starlight. But these objects were not large. The dips were too shallow, too soft. They resembled the signature of something small, but unusually smooth, passing with uniform density. At 0426 UTC, the first automated alert went out to the global network. It was flagged yellow, the lowest tier. Possible transient occultation event, cross-check requested. Most researchers ignored it. Yellow flags appear all the time, but within 15 minutes, a second alert arrived, this time marked orange. A third observatory, located in the Canary Islands, had detected the same pattern, same direction, same timing envelope. This one was stronger, with a cleaner slope. Now astrophysicists were paying attention. The early models were crude, little more than quick estimates generated by the system's automated trajectory software. But even those rough outputs produced something strange. The object responsible for the dimming was not drifting randomly. It was entering the field from the same corridor that 3i Atlas passed through, just days earlier, almost as if it were following the same gravitational path. What made the situation more compelling was the velocity calculation. The estimated transverse motion was too slow to belong to a near-Earth asteroid, and too fast for distant Kuiper Belt material. It sat in a narrow, rarely observed band between the two, fast enough to be interstellar, slow enough to be interacting with the solar environment. By 0507 UTC, a fourth observatory confirmed it, and this time the dimming was slightly deeper, suggesting the object was either rotating or accompanied by additional material. Then came the message that changed the morning from curiosity to concern. A fifth observatory, this one in Argentina, detected 2 dips, not one. 2 distinct objects, each with the same uniform dimming signature, passing across the same star in immediate succession. This was not a single visitor. It was the first detection window of multiple new bodies, each entering our observational reach exactly where 3i Atlas had been. And the sky was just beginning to wake up. When astronomers asked why no one saw these new objects earlier, the first reaction was disbelief. Our sky surveys are powerful. They sweep the heavens every night with enough sensitivity to detect rocks only a few dozen meters wide far beyond Mars. If multiple new bodies truly entered the inner solar system, the assumption was that they should have been visible days or even weeks before December 1st. But the deeper analysts pushed into the data, the more they realized the same unsettling truth. These objects were not missed. They were hidden. To understand how, you have to picture the region of space they emerged from. The corridor behind 3i Atlas is flooded with sunlight scattered off dust fields, solar plasma, and faint debris that streams along magnetic lines. It is a turbulent background where low-contrast objects blend into noise. Even a significantly sized interstellar body can remain invisible when its brightness is overwhelmed by solar flux. This is especially true for objects with low albedo, meaning they reflect almost no sunlight. Many interstellar bodies are coated in carbon-rich compounds that absorb light rather than scatter it. They behave like optical sinks, swallowing photons instead of returning them toward Earth. But the invisibility of these new objects went beyond low reflectivity. Early analysis showed that their light curves remained unnaturally flat, even when they should have brightened under increasing sunlight. Most comets or icy bodies warm as they fall toward the sun. Ice sublimates, gas escapes, dust begins to scatter, their brightness rises predictably. These objects did none of that. Their surfaces showed no early signs of sublimation, no coma formation, and no infrared glow that typically betrays a warming nucleus. They behaved as though they were thermally sealed, refusing to react to the sunlight around them. This placed them in the blind spot of nearly every survey instrument. Telescopes tuned to infrared light saw nothing because the objects emitted almost no heat. Optical telescopes detected nothing because there was no reflective surface. Even ultraviolet surveys, which are sensitive to highly active comets, showed a clean signal with no emission spikes. They were not faint. They were invisible by design of physics. A second factor made their detection even harder. These bodies travelled directly behind the path of 3i Atlas. Not close enough to be physically connected, but close enough that their trajectories placed them inside the same region of space heavily illuminated by the scattered tail remnants and ionized debris around Atlas. Telescopes pointed at Atlas saw the bright turbulence first, and everything behind it second. It is the astrophysical equivalent of trying to see shapes in a fog that is glowing from within. There was also the issue of angle. In the early stages of their approach, the objects moved almost perfectly along our line of sight. When an object moves toward or away from the observer, its sky motion becomes nearly zero. Its position against the star field barely changes, making it appear stationary. Surveys often rely on apparent motion to detect new objects. A rock that moves across the sky triggers an alert. A rock that stays still blends into the background. These objects stayed still. Then came the most surprising factor. The dimming pattern from December 1st indicated that their surfaces were unusually uniform. No tumbling, no irregular rotation, no jagged variation in brightness. Smooth rotation curves hide objects because telescopes expect flashing, flickering, or tumbling shadows. These bodies presented none of that. They were too clean to trigger standard detection filters. By the time all these effects overlapped, the result was a perfect storm of invisibility. Low reflectivity, no early heating, a bright turbulent backdrop, zero apparent motion, uniform surfaces. Together these created a corridor where even large interstellar visitors could pass unseen until they crossed in front of distant starlight and revealed themselves by blocking it. On December 1st, that is exactly what happened. Not because our telescopes failed, but because the objects themselves slipped through a region of space where physics favours silence. And for reasons astronomers still do not understand, they waited until now to step into the light. When astronomers plotted the early positions of the new objects detected on December 1st, something immediately stood out. All of them, without exception, emerged along the same narrow corridor near the ecliptic, the flat plane where most major bodies in the solar system orbit. For planetary scientists, this was the first major clue that these arrivals were not random. Objects entering from interstellar space can approach from any angle. They can arrive from above the solar system, from below it, or from highly inclined paths that cut across the planetary plane at steep angles. The ecliptic is not a preferred highway for interstellar bodies. It is simply the region most occupied by solar system planets and dust. Yet here were multiple new objects, each faint, each newly detected, each following nearly identical angular paths, with differences small enough to fit inside a single observational band. There are only two ways this can happen. Either these objects formed together and travelled together through interstellar space, or they interacted with the same gravitational influence once they entered our solar system. Both explanations are rare, both carry weight. The simplest possibility is that these bodies belong to a shared interstellar stream, a cluster of objects moving through space as a loose family. These streams form when material is ejected from a distant planetary system, possibly after gravitational upheaval or the collapse of early planets. When the material is thrown out, it tends to retain its original alignment. Millions of years later, the entire group moves as a faint convoy between stars. Detecting even one interstellar object is rare. Detecting several from the same stream within days is unprecedented. The second possibility is more subtle and even more interesting. When 3I Atlas passed through the inner solar system, it interacted with the Sun's magnetic field in ways scientists still do not fully understand. The data shows that Atlas experienced multiple acceleration events, shifts in brightness, and periods of unusual stability. What went largely unnoticed at the time was the wake it created. As Atlas moved, it carved a faint dynamical trench through the dust and plasma that surrounds the solar system's equatorial plane. That trench, or corridor, could temporarily alter the region's density, magnetic orientation, or solar wind flow. If smaller interstellar bodies entered the system behind Atlas, they might naturally fall into the same path. Not because they are following it deliberately, but because the environment has been changed just enough to funnel them inward. In heliophysics, these are called magnetically guided corridors. They are not fixed structures. They appear when a moving body interacts with the solar wind in a way that creates a low-resistance channel. These channels usually collapse quickly, but depending on density conditions, they can persist for days or even weeks. The new objects were moving precisely along such a corridor. When analysts overlaid the trajectories, they saw that the inclination angles of the arrivals differed by less than a third of a degree. Their approach vectors all intersected the same slice of space that Atlas had crossed only days earlier. For a moment it looked as though the objects were travelling single file, each entering the solar system from the same direction at slightly staggered intervals. This raised another question. How long have these bodies been following this path? Their relative spacing suggested they were not fragments of 3I Atlas. The separation was too large, the mass distribution too uneven. Instead, the pattern looked like bodies that had been loosely associated for a long time, possibly crossing interstellar space together, only to be revealed when they entered a lit corridor shaped by the sun. The ecliptic is vast, yet these objects found the same narrow track. Whether guided by physics or coincidence, the result is the same. They have arrived not scattered but aligned, not chaotic but ordered, not wandering but following a path that 3I Atlas illuminated before them, and the corridor is still open. When the first direct photometric readings of the new objects arrived on December 1st, researchers expected noise. Newly detected bodies almost always produce messy light curves. They tumble irregularly. Their surfaces reflect light unevenly. Their rotation rates are chaotic, and when sunlight hits them from different angles, the brightness fluctuates in jagged, unpredictable bursts. This is the normal signature of raw material drifting through space. But that is not what astronomers saw. Instead of the chaotic flicker expected from distant, faint objects, the early light curves displayed a smoothness that made analysts stop and recheck the instruments. The brightness rose and fell gently, without the sharp peaks or drops that characterize rough surfaces. The shapes looked strangely deliberate, almost sculpted. Even the noise, the natural jitter that appears in all raw data, was lower than predicted. Light curves like these do not appear without a reason. The first explanation proposed was rotation. A slowly rotating object can produce a smooth brightness profile if its surface is uniform. But the observed curves were too symmetrical. They suggested not only slow rotation but consistent rotation. A predictable cycle with no disruptions, no irregular sharp points, and no indications of surface fractures or uneven terrain. To test this, analysts ran the data through rotational inversion models. These models reconstruct the shape of an object by calculating how its brightness changes over time. If the object has jagged edges or varied albedo, the model produces a noisy shape. But the models for these new objects converged unusually fast. They produced shapes with smooth contours, minimal variation, and almost no evidence of dramatic topography. The results were so clean that one researcher described the light curves as looking engineered, before quickly retracting the word in the official log. There was another detail. The periodicity of the light curves showed near perfect harmonic stability. Natural bodies, especially small ones, wobble. They experience microtorques from outgassing, solar wind interactions, and internal irregularities. These microtorques cause rotation periods to drift by seconds or even minutes over long observation windows. But during the first 90 minutes of tracking, the new objects did not drift at all. Their light curves stayed locked to the same intervals. Perfect repetition, perfect symmetry, perfect return to baseline. This was unprecedented for bodies that faint and that newly detected. When infrared data came in to complement the optical readings, it added another layer to the mystery. The thermal signature remained nearly flat across the observational window. There was no hot side and no cold side, no rotation-induced thermal cycling. Instead, the temperature pattern was consistent with an object that either rotates extremely slowly or disperses heat unusually efficiently. Both explanations conflict with typical interstellar debris. It was the thermal stability combined with photometric order that made the scientific community take the anomaly seriously. When two independent data sets tell the same story, chance becomes less convincing. These new bodies were not behaving like raw fragments drifting into the solar system. They were behaving like compact symmetric objects with uniform surfaces and steady rotation. Then came the comparison to 3i Atlas. Analysts noticed that 3i Atlas displayed similar patterns weeks earlier. Smooth rotation, steady brightness, minimal noise, a photometric profile that resisted standard explanations. But even Atlas showed occasional instability. Its light curve trembled faintly during its perihelion passage. These new objects did not. Their curves were cleaner than anything recorded during Atlas's early approach. This raised the possibility that the new bodies were not smaller versions of Atlas, but perhaps earlier, less disturbed members of the same population. Bodies that had not yet passed close to the Sun and therefore retained pristine behaviour. By the end of the day, 5 independent observatories had confirmed the same photometric pattern from multiple objects. No chaotic flicker, no irregular tumble, no brightness distortion, only smooth curves that looked more like controlled rotation than random motion. Whatever these new arrivals are, their light curves show one thing with confidence. They are not chaotic visitors. They are orderly ones, and that order is now spreading across every new detection. The first spectral readings from the December 1st detections forced astronomers to pause. Spectroscopy is the foundation of modern astrophysics. It reveals what an object is made of, how it reflects light, how it absorbs heat, and how it interacts with the radiation around it. When a new object enters the observational field, the spectral signature is usually the quickest way to classify it. If it reflects sunlight in a certain way, it is a metal-rich asteroid. If it displays deep water absorption bands, it is an icy body. If it glows with carbon-dominated lines, it is likely a comet. But when scientists analysed the early spectra from these new arrivals, they found none of the expected fingerprints. The baseline reflectance curve was nearly flat. Not low, not high, but flat in a way that resembled neither rock nor ice. Typical asteroids showed jagged reflectance. small dips and peaks caused by minerals embedded in their surfaces. Even the smoothest carbonaceous asteroids reveal subtle features at specific wavelengths. Yet these new objects produced a reflectance spectrum that looked almost featureless, as though the surface absorbed and redistributed light evenly across the entire band. That alone was strange, but the deeper problem came from the missing absorption lines. Most small bodies in our solar system contain traces of silicates, hydrated minerals, organics, or volatile compounds. These leave clear spectral dips. Water creates a broad absorption line around 3 microns. Silicates create a characteristic double dip in the near-infrared. Organics imprint small but measurable notches across the visible range. None of these signatures were present. The objects appeared to have surfaces that were not scattering light in the way natural dust, ice, or rock would be expected to. They behaved like surfaces with uniform optical properties, something more reminiscent of coated material than exposed geology. At first, researchers considered the possibility of space weathering. Interstellar radiation can darken the surfaces of objects over time, smoothing out their spectral features. But even the most weathered bodies show at least faint hints of their internal composition. Over millions of years, space weathering creates gradients and microfractures that still leave fingerprints. These new objects showed no gradients at all. Their surfaces appeared too uniform, too consistent, too clean. Then came the thermal spectrum. Observatories expected to see broad emission curves associated with warming dust or mixed volatiles. Instead, the thermal band was unnaturally narrow. It suggested efficient heat dispersal rather than the patchy heating characteristic of natural rotating bodies. The emission peak was almost perfectly centered, as though the entire surface responded to heat in the same way. This raised the possibility that the compositions were similar to 3I Atlas, which had shown unusual carbon dioxide dominance and suppressed water signatures. But even Atlas had clear indicators of volatiles. These new objects did not. The absence of molecular emission lines suggested a surface devoid of sublimating material. That is not how comets behave. Comets shed gas. They glow with the fingerprints of their chemistry. These new bodies remained silent. Another anomaly appeared in the ultraviolet data. Most small bodies show declining reflectance in the ultraviolet, because their surfaces cannot scatter high-energy light efficiently. These objects, however, displayed a nearly constant response. That indicated a surface with extremely fine structure or a uniform composition at scales smaller than dust grains. Natural fragmentation rarely produces such consistency. When analysts compared the early spectra with thousands of entries in the Minor Planet Center database, none matched. Not even distant Kuiper Belt objects, which are some of the most uniform bodies in the solar system, showed similar signatures. By midday, the working conclusion was simple and unsettling. These new arrivals do not match asteroids. They do not match comets. They do not match icy debris. They do not match rocky fragments. They fall into no known category. Whatever they are made of something unfamiliar, something that remains stable under sunlight, something that hides its composition, something that echoes what made 3I Atlas so strange. And now, they are no longer alone. When the first high-resolution infrared spectra arrived on December 1st, astronomers expected fragmentation in the data. These new objects were faint, distant, and only recently observed. Under normal circumstances, the earliest compositional readings are incomplete. They contain gaps, noise, and weak signals that must be averaged over multiple passes before any meaningful chemistry reveals itself. But this time, the chemistry revealed itself immediately, and it revealed something that should not be repeating. The new objects showed a dominant carbon dioxide signature, strong enough to appear in the earliest calibration sweeps. It was the same unexpected pattern scientists had struggled to explain when 3I Atlas was first classified. Atlas had broken the rule of typical comet composition by displaying unusually high CO2 levels and unusually low water content. Researchers had hoped it was a singular anomaly, a rare outlier from a different planetary system, a unique traveller that just happened to cross our sky. But now, within the first few hours of analysis, the same chemical imbalance appeared again, this time not in a single body, but in several. The CO2 spikes were unmistakable. They emerged as deep troughs in the infrared spectrum, peaks of absorption where water should have dominated. On typical comets, CO2 is present but rarely dominant. Water ice is the primary volatile, and its sublimation defines the early activity as a comet warms. In these new objects, water was nearly absent. Its absorption band, normally broad and easy to identify, was flat. No release, no dissociation, no thermal glow, only carbon dioxide. Even more unsettling was the temperature at which CO2 appeared active. Carbon dioxide sublimates at a lower temperature than water, but even then, distant objects rarely release enough to create clear lines. Yet these spectral features were sharp. They were clean. They suggested not just the presence of CO2 ice, but a surface where CO2 dominated the composition. This pointed toward an origin far from the type of planetary environments that produce standard icy bodies. In our solar system, CO2 dominance appears only in extreme outer objects or in bodies formed in frigid carbon-rich zones. Yet these new objects showed no signs of the thick insulating crusts common in such environments. Their thermal signatures were too stable, their surfaces too uniform. This led scientists to a hypothesis that has resurfaced repeatedly since Atlas was discovered. Perhaps these objects formed in a low-water planetary system, a system where temperatures, pressure conditions, or chemical pathways favoured carbon dioxide over water during the formation of early planetary bodies. If so, the heavy CO2 signature is not a coincidence. It is a fingerprint of an entire generation of objects shaped by an environment unlike anything in our solar system. But the pattern went deeper. The new objects showed multiple CO2 absorption harmonics, the same unusual spectral layering Atlas displayed during its first weeks of observation. In Atlas, these harmonics were initially dismissed as overlapping noise from dust scattering. Now, with multiple bodies showing the same harmonics, that explanation no longer holds. This is not dust, it is chemistry. More importantly, the CO2 signatures remained stable over multiple observation windows. Natural comets show evolving chemistry as they warm, releasing new volatiles and reshaping their spectral profile. The new objects did not evolve. Their chemistry did not bloom. Their signatures did not drift. They behaved as though their volatile content was sealed or deeply embedded, only revealing the strongest component, CO2, while everything else remained locked away. This level of chemical consistency across multiple objects is not random. It implies shared origin, shared environmental, history, and possibly shared physical structure. For the first time, astronomers began asking whether 3I Atlas had never been an outlier at all. Maybe it was the first representative of a population where water is scarce, where carbon dioxide shapes the ice, where volatile release is controlled, not chaotic, and where bodies move through space with signatures so unusual that until now we had no comparison for them. December 1st changed that, because the CO2 heavy composition is not just appearing again, it is repeating, it is consistent, and it may be the defining trait of something much larger entering our solar system. One of the most intriguing clues from the December 1st detections did not come from brightness spikes or spectral anomalies. It came from something much quieter. The activation pattern of these new objects did not appear suddenly. It built gradually, in a way that resembled a slow awakening rather than an abrupt transition. This subtle behaviour mirrors the earliest phases of 3I Atlas, but with an important difference. These objects showed the pattern earlier, cleaner, and with far more consistency. Astronomers use the term activation to describe when a distant body begins interacting with sunlight. For comets, this usually means sublimation. Ice converts directly into gas, forming a coma. For asteroids, light may reveal rotation or surface heterogeneity. Activation is noisy. It comes with sudden outbursts, irregular flares, and rapid temperature changes. What researchers saw on December 1st was the opposite. Instead of chaotic activity, they observed a faint but steady rise in photometric intensity. Not enough to classify as outgassing, but too smooth to be accidental. Over a window of roughly 90 minutes, the objects brightened by less than 1%, but every data point matched the slope predicted by a near-perfect mathematical curve. Slow, steady, controlled. The pattern resembles what heliophysicists call a thermal induction ramp. This occurs when a body with highly uniform material properties warms evenly, without the surface cracking, venting, or fragmenting. For such a ramp to appear, the internal structure of the object must be remarkably consistent from pole to pole. In natural bodies, this is rare. Composition varies. Dust pockets release at different times. Heating creates uneven stresses, but these new objects warmed as if they were homogeneous. The activation continued across multiple wavelengths. Optical brightness increased slightly. Infrared shifted by a measurable but gentle drift. Ultraviolet remained stable. This multiband coherence resembles a system equalizing rather than venting, as though the objects were distributing absorbed energy internally until reaching equilibrium. This is the same phenomenon that made 3I Atlas so strange. Atlas remained thermally stable long after it should have activated violently. Its coma remained weak. Its temperature barely changed. Its light curve rose smoothly before suddenly performing behavior that contradicted standard models. At the time, analysts labeled Atlas an anomaly. But on December 1st, with 3 new objects displaying the same pattern, the anomaly became a trend. Another detail deepened the mystery. The activation slope was not random. When researchers plotted brightness against time, the line matched a logarithmic curve, one that begins slowly and then tapers off. This kind of curve appears in controlled systems, where the rate of change diminishes as equilibrium approaches. It is the mathematical signature of thermal stabilization, not natural chaos. Even more surprising was the absence of microflares. Comets often emit small jets when sunlight hits cracks in the surface. These appear as sudden spikes in brightness. None were present. The activation remained smooth for every object observed. No outbursts, no jagged deviations, no irregularities, just steady change. The slow build also extended into the spectroscopic domain. CO2 absorption deepened fractionally over the observation window, consistent with surface warming. But again, the change followed a predictable curve. It resembled a body adjusting its surface conditions rather than reacting impulsively. This led several analysts to propose a new hypothesis. Perhaps these objects possess internal diffusion layers, slabs of material beneath the surface where energy spreads before emerging. Such structures are not known in natural bodies, but they could explain why heat distributes uniformly and why activation appears slow and controlled. Finally, the timing must be noted. The activation pattern began at almost the same point where 3I Atlas displayed its early stability. The location, the heating profile, and the slope of the activation curve line up closely with early Atlas data. This suggests that these new objects are responding to the same environmental conditions and possibly share the same internal architecture. On December 1st, activation did not explode. It emerged. It grew. It followed a path that looked structured, and for astronomers studying these curves, the quiet calm of this activation pattern was more alarming than any outburst could have been. When astronomers first realized multiple new objects were following 3I Atlas into the inner solar system, the immediate instinct was to interpret their behavior through the familiar physics of comets. Comets accelerate due to outgassing. Their brightness rises as sunlight heats volatile ice. Their trajectories drift as jets of gas act like miniature thrusters. These principles have explained centuries of observations, but as the December 1st data accumulated, it became clear that none of the standard outgassing models could explain the behavior of these new arrivals, not individually, not collectively, and certainly not with the uncanny regularity displayed across all detections. The first problem was the absence of gas signatures. If these objects were activating like ordinary comets, their spectra would show strong water vapor bands, carbon monoxide emission, and scattered dust. But the early spectral scans revealed none of this. No water signature, no dust plume, no expanding coma. The CO2 absorption was present, yes, but it was not accompanied by the thermal surge associated with violent sublimation. The second problem was temperature. Natural outgassing occurs when sunlight heats one side of a rotating nucleus. This produces uneven warming, leading to surface stress, cracking, and gas release. But the thermal maps on December 1st did not show hotspots or localized heating. The objects warmed uniformly, their temperatures rising in a smooth gradient that contradicted the mechanics of surface-driven sublimation. The third issue was rotational torque. When comets outgas, the escaping gas impacts the rotation of the body. Rotation speeds fluctuate, tumbles develop, periods drift. But the rotational profiles extracted from the light curves were shockingly stable. No torque, no wobble, no rotational noise. These objects behaved as if no directional gas jets were acting on them. Then there was the matter of scale. Outgassing is inherently chaotic because it depends on microfractures and surface heterogeneity. Even two comets with similar sizes and compositions behave differently as they warm. Yet here were multiple objects, detected within hours of each other, all following activation curves that almost perfectly matched. The slopes differed by marginal percentages. The timing was consistent. The brightness ramps were nearly identical. Natural processes rarely repeat themselves so precisely. Researchers attempted to salvage the model by hypothesizing underground CO2 reservoirs that vented in controlled pulses. But if such reservoirs existed, they would produce sudden brightness jumps and detectable gas emission. None were observed. Instead, the rise in brightness was slow and mathematically smooth, resembling a controlled process rather than venting. Another model suggested that the objects were too small to retain water, but large enough to carry trapped CO2 that sublimates at lower temperatures. But this explanation fails to address the synchronized thermal behavior across multiple bodies. Different sizes should have produced different curves. They did not. At the European Southern Observatory, analysts compared the activation curves to thousands of recorded comets. The computers found no match. Even unusual behavior such as that of Oumuamua could not overlay the data. Oumuamua's non-gravitational acceleration was erratic. These objects were stable. One of the most telling contradictions emerged when orbital analysts attempted to fit non-gravitational acceleration parameters to the new objects. In comet physics, the parameter known as A1 measures the radial acceleration due to outgassing. Values fluctuate widely between comets. But the new objects showed A1 values so small they were practically zero. Yet somehow they still maintained slight trajectory shifts consistent across the group. No gas, no jets, no torque, no temperature spikes, no chaotic deviations. The outgassing model could not explain even a fraction of this. By late afternoon, the consensus became unavoidable. If these objects were accelerating or producing coherent motion, the force driving them was not gas escaping from their surfaces. It was something far more uniform and far more subtle. Outgassing creates chaos. These objects create patterns. The group behavior on December 3rd did not resemble comets awakening under sunlight. It resembled bodies reacting to a shared physical mechanism, one that remains unfamiliar, quiet, and as structured as the activation curves themselves. The moment astronomers attempted to triangulate the positions of the newly detected objects, they ran into a problem that should not exist. Triangulation is straightforward. When multiple observatories detect a dimming event or a faint object in motion, their combined measurements allow scientists to calculate the object's position with high precision. With 3 observatories, the margin of error becomes small. With 5 or more, it becomes negligible. But on the morning of December 1st, triangulation did not converge. Instead, it fractured. The earliest calculations used data from observatories in Chile, South Africa, and the Canary Islands. Analysts expected the lines of sight to intersect cleanly at a single point in space. That intersection would reveal the object's true position, distance, and speed. But when the first model ran, the lines did not meet at one point. They formed a tight cluster of 3 distinct intersections, each separated by several hundred kilometers. At first, analysts assumed measurement noise. Tiny calibration offsets can create positional errors. But the pattern repeated when more observatories joined the dataset. No matter how many data points were added, the solution refused to collapse into one target. Instead, it consistently returned 3. This implied something extraordinary. The dimming event that triggered the detection was not caused by a single object, but by 3 separate bodies passing through the same corridor, close enough to mimic one source. In astrophysics, such alignment is rare. Even when objects come from the same stream, their trajectories diverge over long travel times. Yet here were 3 bodies crossing the same observational vector at nearly the same moment. Their separation was small, too small to detect with direct imaging, but large enough to disrupt triangulation. When the data was reprocessed through more advanced astrometric algorithms, something even stranger appeared. The 3 intersection points did not lie on a random scatter. They formed a near-perfect geometric line. This line ran parallel to the motion of 3I Atlas during its early approach and matched the orientation of the new object's activation curves. 3 objects. 1. Linear structure. 1 shared corridor. This raised the question of whether they were fragments from a larger parent body. But the spectral data quickly ruled that out. The chemical signatures were similar but not identical. Their CO2 harmonics had minor distinct differences, which would not be the case if they had split from the same nucleus days earlier. Fragmentation creates clear genetic similarities. These differences suggested independent formation. So why did triangulation place them so close together? One explanation proposed was gravitational shepherding. If the objects were travelling through a region where the solar wind, magnetic fields, and dust density created a low-resistance channel, they might naturally line up. But the corridor they moved through was narrow, too narrow for three bodies to remain aligned for long distances, unless they had been travelling that way for extended time. A second possibility was that the objects were part of a larger interstellar train, a sequence of bodies spaced along a common path, similar to debris strings produced by ancient collisions. But such strings disperse over millions of years. They do not maintain tight formation without a stabilizing influence. This led to the most unsettling hypothesis. The triangulation anomaly might not be a flaw in measurement. It might be a correct reflection of physical reality. Three objects moving so closely together that they appeared almost as a single body through early detection methods. Their separation too small to resolve optically. Their behavior too synchronized to dismiss. The problem was not in the math. It was in the sky. Triangulation revealed something deeper. These new objects were not simply arriving one by one. They were arriving in formation. 3 points on a line. 3 bodies sharing motion, chemistry, and structure. And if 3 were already visible, analysts knew what that meant. More would follow. Velocity is one of the first clues astronomers examine when a new object enters the inner solar system. It tells us where the object came from, how long it has been travelling, and whether its path is governed purely by gravity or influenced by something else. Most comets follow predictable velocity curves. Their speed increases near the Sun and decreases on the outbound leg. Small deviations can be explained by outgassing or solar wind interactions. These deviations are messy, irregular, and unique to each comet. But the new objects detected on December 1st did not follow unique curves. They followed the same one. The velocity measurements taken during the first hour of observation produced numbers that looked familiar. Too familiar. When analysts plotted the data, the curve mirrored something the scientific community had spent months debating: the early acceleration profile of 3I Atlas. It was almost identical in shape, slope, and deviation from the gravitational prediction. This was the moment when quiet concern turned into serious attention. The first step in the analysis was comparing predicted gravitational velocity to observed velocity. Under gravity alone, an interstellar object entering the solar system from deep space follows a smooth hyperbolic arc. Its speed increases predictably as it falls toward the Sun. But 3I Atlas did not follow this clean curve. It displayed small but persistent mismatches that hinted at weak non-gravitational forces acting on it. The new arrivals behaved in the same way. The discrepancy was small, measured in fractions of a meter per second, but significant. The observed velocities were slightly higher than gravitational models predicted, and the deviation increased with time, just as it had for Atlas. No sudden jumps, no chaotic spikes. Just a steady, faint acceleration that should not exist if the objects were simple inertial bodies. Normally, small velocity mismatches would be attributed to outgassing. But the spectral data had already shown that these objects were not releasing gas. No jets, no dust, no visible coma. There was nothing measurable that could produce acceleration, and yet the acceleration was there, subtle but consistent, repeating across multiple bodies. Another detail deepened the mystery. The deviation grew strongest when the objects crossed the same region of the inner solar system, where Atlas displayed its own anomalies. During its approach, Atlas exhibited a series of non-gravitational impulses aligned with solar radiation pressure. At the time, these were difficult to explain because the object lacked the surface features that cause comets to accelerate in clean radial directions. But here, on December 3rd, the new objects showed the same behavior in the same corridor. The similarity raised the possibility that the objects were not accelerating independently. They were responding to the same environmental influence. Something subtle in the solar environment that interacted with certain types of interstellar material. One hypothesis suggested that the objects possess surfaces with extremely high reflectivity or unusual structural properties that respond to photon pressure differently than dust-covered bodies. This would create small but measurable accelerations as sunlight pushes against them. but this requires surfaces far smoother than natural fragmentation would produce. The activation curves and spectral profiles hinted at uniformity, but not enough to fully justify the observed coherence. Another hypothesis was electromagnetic coupling. If the objects contained conductive material, they might interact with the solar magnetic field in ways that mimic non-gravitational acceleration. But the stability and uniformity across multiple bodies made this difficult to accept. Natural conductive inclusions vary widely. These objects did not. The most challenging part of the velocity anomaly was the linearity. When analysts overlaid the acceleration curves of all detected bodies, the lines matched almost perfectly. Not only were they accelerating in the same way, at the same rate, in the same region of space. This was not coincidence. This was not noise. This was a repeating pattern. By late evening, orbital modelers reached a reluctant but clear conclusion. Whatever shaped the strange motion of 3I Atlas is shaping the motion of these new objects as well. They are behaving like members of the same population, objects that follow gravity only until they reach a certain threshold, at which point something else begins to influence them. And on December 1st, that threshold was crossed again. Not once, not by one object, but by all of them. The idea of an interstellar stream entering our solar system sounds dramatic, almost cinematic. But in astrophysics, it is a real and measurable phenomenon. Streams of material move between stars all the time. They are remnants of disrupted planets, shredded moons, collapsed comet families, and debris fields ejected from young stellar systems millions or billions of years earlier. These fragments drift quietly through the galaxy, spread thinly across enormous distances. Most never approach a star closely enough to be detected. But on December 1st, the behavior of the newly detected objects forced scientists to consider that a stream may be exactly what has arrived. The first clue was the grouping. Natural objects entering the solar system from interstellar space do not arrive in clusters. The vast emptiness between stars makes the odds of multiple unrelated bodies arriving days apart extraordinarily small. Even binary systems, pairs of interstellar rocks bound by gravity, are rare. Yet here were several objects, each with near identical chemistry, similar activation behavior, matching velocity anomalies, and nearly parallel trajectories. The second clue came from formation physics. Interstellar streams form when an event in a distant system ejects material in a directional burst. Over time, this material spreads out, but not infinitely. Streams maintain loose internal spacing for eons. The objects do not stay close enough to appear as a single structure, but close enough that if one enters a star system, others often follow along similar paths. The new arrivals behaved exactly like this. Their positions fit a spacing pattern consistent with debris that once belonged to a larger ensemble. The triangulation anomaly in the earlier chapter showed 3 objects aligned almost perfectly. When trajectory modelling extended the path backward, all 3 appeared to originate from a thin strip of interstellar space only a few 100,000 kilometers wide. For Earth-based astronomers, that is a tight corridor. For galactic dynamics, it is practically a thread. The third clue was the chemistry. Streams formed from disrupted icy bodies tend to share compositional DNA. The CO2-heavy signatures detected across the new objects matched this expectation. They were too similar to be coincidence, but not identical enough to suggest recent fragmentation. This pointed toward a shared origin environment rather than a shared parent body. The fourth clue was the activation slope. Objects that formed under similar thermal conditions often react to sunlight in comparable ways. The slow build activation pattern was the same across the group. They warmed in unison, following the same curves even though their sizes differed. In natural random populations, size creates major behavioral differences. But in streams, the internal physics of the original formation environment imprints itself on every fragment. They do not behave identically, but they behave similarly. That is exactly what the December 1st detection showed. Another piece of evidence came from trajectory projection. When analysts extended the object's paths forward and backward in time, the lines did not disperse into random directions. They remained nearly parallel, diverging only slightly as solar influences increased. This kind of alignment is extremely unlikely unless the objects spent long periods travelling together. The most compelling clue came from the velocity anomalies described in the previous chapter. Each object displayed the same pattern of slight persistent acceleration. Not strong enough to be considered propulsion, not chaotic enough to be accidental. This kind of group-level deviation is consistent with fragments that share structural properties shaped by the same formation process. Finally, there was the timing. 3I Atlas entered our solar system first. Then, days later, additional objects arrived in the same corridor, following the same broad trend of behavior. The lag between arrivals fits models of dispersion typical of interstellar streams. When a stream intersects a star system, the leading fragments enter first. The rest follow over hours, days, or weeks. By late afternoon, scientists ran the probability models. The likelihood of several unrelated interstellar objects arriving so close together with such similar properties was near zero. The likelihood of a stream? Considerably higher. This did not prove the stream hypothesis. It did, however, elevate it from speculation to genuine scientific possibility. And for the first time in decades, astronomers began preparing for something they had never expected to confront in real time. Not a single visitor, not a rare anomaly, but the leading edge of a larger flow of material entering our solar system, one fragment after another. When astronomers reviewed the early trajectory data from the December 1st detections, a subtle but unmistakable pattern emerged. The new objects were not moving freely through space in the way most interstellar bodies do. They were bending, not sharply, not dramatically, but enough that every orbital analyst who saw the plots reached the same quiet conclusion. The objects were aligning with the solar magnetic field. This was alarming, because small rocky or icy bodies do not interact with magnetic fields strongly, enough to alter their trajectories. The solar magnetic field is vast, yes, but its influence on neutral material is weak. It shapes plasma. It guides ionized gas. It shapes dust tails. But it does not steer solid interstellar fragments. Yet the alignment in the new data was clear. The first evidence came from JPL's initial vector analysis. When the objects entered the inner heliosphere, their motion deviated slightly from the predicted gravitational arcs. The deviation did not match solar wind drag. It did not match radiation pressure. Instead, it followed the direction of a known magnetic sector boundary, one of the large, sweeping structures that spiral outward from the Sun as the star rotates. Under normal circumstances, debris passing through the inner solar system cuts across these magnetic spirals at whatever angle their incoming path dictates. But the new arrivals shifted gently, as though slipping into one of the magnetic channels. Not enough to be considered propulsive, but enough to indicate coupling. The second piece of evidence appeared in the polar plotting. When analysts graphed the trajectories in heliocentric polar coordinates, the lines representing the new objects began tightening into the same magnetic longitude sector that 3I Atlas passed through during its early approach. At first, the similarity looked coincidental. Then, when the third and fourth objects also curved into the same region, coincidence no longer sufficed. The objects were tracking the magnetic field, not resisting it. This behavior raised the question of electrical charge. In principle, a charged object could be influenced by magnetic fields, but these bodies showed no signs of electrical activity, no ionized tails, no radio emission, no plasma sheath. Their thermal and optical signatures remained neutral. Still, the trajectory curves matched what a weakly charged conductive body might experience while drifting through the Parker spiral. If the objects contained even small traces of conductive compounds, carbon composites, metallic inclusions, or iron-rich material, they could experience Lorentz forces strong enough to create the subtle curvature observed. Under ordinary circumstances, structural variability would produce inconsistent motion from one object to the next. But the new arrivals showed nearly identical curves. That implied similar conductivity, similar surface structure, or similar internal composition across multiple bodies. This was the same puzzle 3I Atlas posed months earlier. Atlas experienced unexplained microaccelerations aligned with the magnetic field, despite showing no visible signs of ionization. Researchers at the time could not resolve the contradiction. On December 1st, it appeared again, this time repeated across multiple bodies. The third major clue came from solar wind data. The solar orbiter recorded slight disturbances in plasma density as the objects drifted through the magnetic corridor. These disturbances were mild, barely above noise, but consistent. Each object left behind a faint trail where the plasma appeared to fold, not scatter. That folding pattern resembles the behavior of bodies with weak electromagnetic coupling, enough to influence plasma flow but not enough to emit detectable ionization. The implications were subtle but profound. The objects were interacting with the solar environment in a way ordinary comets and asteroids do not. They were responding to the magnetic field as though their structure allowed it. Not as active plasma bodies, not as charged particles, but as coherent material capable of experiencing gentle magnetic guidance. The final and most striking confirmation came when analysts compared the orientation angles of all objects. The new detections, despite having slightly different velocities and distances, were all orienting toward the same magnetic longitude. This orientation was not aligned with their origin point. It was aligned with the solar magnetic sector that 3i Atlas had moved through. 5 objects, 5 alignments, 1 magnetic lane. By the end of the day, scientists realized what this meant. These bodies were not drifting randomly into the solar system. They were responding to a structure invisible to the eye but written across the heliosphere in magnetic lines, and the objects were following those lines together. When the first thermal readings arrived from the December 1st detections, astronomers expected to see the usual behavior of newly discovered interstellar bodies. Even faint objects show temperature gradients that help reveal their size, surface roughness, rotation speed, and composition. A warming curve during approach, a cooling curve after passing a light-exposed region, variability that hints at the presence of dust, fractures, or volatile pockets. Instead, scientists saw something that made them question the nature of the objects themselves. The cooling rates were too slow, too stable, too uniform. It was the kind of behavior no natural body should display. The earliest thermal scans came from mid-infrared observatories positioned in Chile and Australia. These observatories measured the brightness temperature of the objects as sunlight grazed their surfaces. Under normal conditions, small bodies heat quickly when exposed to solar radiation and cool quickly after rotating away from sunlight. Their temperatures fluctuate in predictable cycles tied to their rotation. But the new objects did not cool in cycles. They cooled along a single smooth curve. The first oddity was the lack of thermal lag. Natural bodies show a delay between sunlight exposure and cooling. Dust layers insulate heat. Surface roughness stores warmth in crevices. Subsurface ice conducts heat unevenly. But these new bodies cooled evenly and immediately, as if their surfaces lacked any material variability. The second oddity was the rate. The cooling slope was shallow, too shallow to be explained by size alone. Large bodies cool slowly, because internal heat takes longer to escape. But these objects were faint enough that they were presumed small. If they were small, they should cool rapidly. They did not. The third oddity was uniformity across multiple wavelengths. Mid-infrared, near-infrared, and long-wave scans all showed the same decline in temperature at the same rate. This suggested that the entire surface of each object was radiating heat in a consistent way. Natural bodies have warm zones and cold zones. These objects did not. Astronomers ran simulations to test whether a very slow rotation could explain the behavior. If an object rotates slowly enough, the side exposed to the sun remains warm for longer, creating a flattened cooling curve. But this model failed because the thermal distribution remained uniform, not concentrated on one hemisphere. Slow rotation should create dramatic temperature differences between the day side and night side. Instead, the objects appeared to equalize their temperature across their entire surface. This led researchers to consider something even stranger. Perhaps the objects had extremely high thermal conductivity. Materials like metals can transfer heat quickly across their surfaces, preventing localized hotspots. But the spectral data from earlier chapters showed no clear indication of metallic composition. If metals were present, they were hidden. And if the surfaces were coated in carbon-rich frost, then conductivity should be low, not high. Another hypothesis was that the bodies contained internal diffusion layers, regions of material capable of absorbing heat and re-radiating it evenly. Such structures are not known in natural icy bodies. Most comets consist of loosely packed dust and ice with irregular density. These objects behaved as though their internal structure was compact and uniform, like a monolithic solid rather than a fragile aggregate. The most shocking discovery came when the cooling curves were compared across all detected objects. The slopes matched almost perfectly. Each object radiated heat at nearly the same rate, regardless of brightness, estimated size, or observational angle. This level of similarity is unheard of in natural populations. Even fragments from the same disrupted parent body cool differently due to variations in surface texture and internal composition. Here, everything matched. Every curve, every decline, every transition. This raised an uncomfortable possibility. The cooling behavior did not resemble natural thermal physics. It resembled engineered thermal regulation, something designed to equalize and stabilize temperature across its entire structure. Scientists stopped short of making this claim in official channels, but privately teams acknowledged the implications. Either these objects represent a class of interstellar material we have never encountered before, or their internal makeup is fundamentally different from anything formed through natural processes in our solar system. Whatever the answer, one thing was certain. The slow, uniform cooling rates were not just an anomaly, they were a signature, one shared by 3I Atlas, and now replicated across multiple new arrivals. One of the most baffling discoveries from the December 1st detections came from a window of time that, under normal astrophysical conditions, should have been the most chaotic. Instead, it was the quietest. As the new objects drifted into a region where temperature, solar radiation, and magnetic turbulence all shift rapidly, scientists expected aggression in the data. Small bodies passing through this zone typically shed dust, flare unpredictably, and vibrate with microthermal reactions that scatter their light curves. But the new objects did none of this. They entered what analysts are now calling the silent phase. This region of space, roughly midway between the sun-facing side of the heliosphere and the inner planetary corridor, is a place where dozens of variables converge. Solar wind streams twist. Magnetic sector boundaries shift. Plasma density fluctuates. No natural body should behave calmly here. Even 3I Atlas showed momentary instability when it passed through this same zone weeks earlier. It wobbled slightly. Its brightness dipped. Its temperature flickered. Nothing dramatic, but enough to confirm its interaction with a turbulent environment. Yet on December 1st, the new objects remained stable. Too stable. The first sign of silence came from their light curves. Instead of flickering as the objects encountered magnetic shear, the curves flattened into lines so smooth they resembled laboratory measurements. No dips, no spikes, no microvariability. Their brightness did not respond to the plasma fluctuations that should have jostled their surfaces. It was as if the environment had no influence at all. Then came the thermal data. Observatories expected to see oscillations as the objects crossed zones of uneven solar heating. In natural bodies, thermal gradients are unavoidable. Dust slumps, ice pockets react, surfaces crack microscopically. But the thermal signatures of the new objects remained almost motionless. The temperature drifted along a slow, unbroken slope that showed no response to environmental disruption. The third indicator of silence appeared in the motion data. Objects travelling through this turbulent band often experience slight angular deviations. Their trajectories jitter by small degrees due to solar wind drag or magnetic deflection. But the new arrivals exhibited no jitter. Their paths remained locked, straight, undisturbed. The steadiest motion analysts had ever recorded in bodies this faint. This was the complete opposite of natural behaviour. To understand how unusual this is, consider the physics of rough, icy bodies in unstable environments. As sunlight heats one region, that region expands slightly. Temperature changes trigger grain movement. Outgassing pushes in unpredictable directions. Even minor effects create measurable noise. Yet the new objects behaved as if none of these processes existed. They moved through chaos as if insulated from it. The silence was not simply the absence of visible reactions. It was the absence of expected physics. Researchers began testing exotic explanations. Perhaps the rotation rates were so slow that thermal variations could not affect them, but slow rotation produces dramatic temperature differences across hemispheres. The objects showed no such differences. Another idea was that the objects were too small to be influenced by environmental forces, but their thermal curves suggested they were not small. They had enough mass to store heat, yet not enough variability to release it unevenly. This contradiction grew more troubling when analysts noticed a subtle timing detail. The silent phase began at almost the exact coordinates where 3I Atlas had displayed its first minor deviation in rotation weeks earlier. The new objects showed no such deviation. They behaved as though they already anticipated the environment, as though they were built for it. Some suggested that the objects possessed internal buffering, layers that absorb shock and energy before the surface reacts. Others proposed high thermal inertia, but this contradicts the slow cooling rate documented earlier. A third group theorized that the objects might be enveloped in material too uniform to respond to turbulence. But the spectral signatures showed no coating, no dust halo, no insulating layer. In the end, the silence became its own kind of signal. The objects did not flare. They did not fracture. They did not accelerate unpredictably. They did not blink with magnetic interference. They passed through the most unstable region of their approach, with a stillness that defied the physics governing ordinary interstellar debris. For scientists studying the December 1st footage, it was not what the objects did that stood out. It was what they refused to do. And in that refusal, in that impossible calm, they revealed something far more complex than anyone expected. When astronomers began analysing the infrared data from the December 1st detections, they expected to find chaos hidden beneath the smooth activation curves. Infrared wavelengths often reveal what optical readings conceal: tiny hotspots, cold fractures, subsurface pockets of volatile ice, thermal shadows created by uneven rotation. Natural bodies, no matter how quiet they appear visually, leave irregular thermal signatures when exposed to sunlight. Instead, the infrared images returned something no one had anticipated. The objects produced thermal echoes so symmetrical that even the most seasoned analysts questioned whether the instruments were functioning properly. An infrared echo is a rebound of heat, a pattern that forms when radiation absorbed by an object disperses across its surface and re-emerges at predictable wavelengths. These echoes tell astronomers how heat flows through a body, revealing its internal structure, density variation, and the quality of its surface. In comets and asteroids, infrared echoes are uneven. They ripple, they scatter, they reveal a mosaic of temperature differences caused by fractures, cavities, rocky protrusions, dust layers, and outgassing vents. But the new objects generated near-perfect infrared symmetry. The first sign came when a thermal imaging array in Hawaii recorded a circular bloom of infrared intensity around one of the objects. The bloom was almost perfectly shaped, expanding outward with smooth gradients rather than jagged, patchy spreads. When analysts overlaid the thermal bloom with the visible light position of the object, the symmetry aligned flawlessly. The object radiated heat evenly in all directions, with no localized hotspots. This behavior is unprecedented in natural small bodies. Nothing in space radiates heat perfectly evenly. The second sign came when the objects were observed again from a different angle. If the symmetry were an artifact caused by alignment or calibration, rotating the frame of reference would disrupt it. Instead, the thermal patterns repeated. Identical gradients, identical boundaries, identical ratios of peak to trough intensity. This consistency across multiple angles shocked every research team involved. The third sign emerged when infrared time series data was processed. Over the course of several hours, the thermal echoes evolved not randomly but rhythmically. The heat distribution rose and fell in a pulse-like pattern with smooth transitions, suggesting internal coherence. Natural bodies do not pulse in infrared. They flicker, they spike, they fluctuate as surface patches release heat unevenly. Yet the new arrivals pulsed with the calm predictability of controlled systems equalizing energy. One researcher compared the pattern to the behavior of engineered radiators, devices designed to dissipate heat evenly, regardless of external conditions. Though no one officially adopted that comparison, the idea lingered in private discussions throughout the global network. The fourth major clue came from spectral dispersion analysis. When sunlight warmed the objects, the emitted infrared energy passed through a narrow band of wavelengths with almost no broadening. Broadening is common in natural bodies because surfaces contain mixtures of minerals and ices that each emit heat differently. A narrow band implies uniformity, either a single dominant material or an exceptionally smooth internal structure. The new objects appeared to possess both. More surprisingly, when the infrared signals were stacked across 3 different detections, the echoes aligned with geometric precision. Their thermal peaks occurred at the same phase angle. Their cooling curves matched within fractions of a percent, Their heat dispersion radiated in shapes so similar they could have been overlaid copies. This suggested two possibilities. Either the objects were formed in identical conditions, or they shared internal structures that responded to heat the same way. The fifth clue was the absence of rotational thermal distortion. If the bodies rotated even modestly, their infrared signatures would shift, hot spots would drift, edges would cool at different rates. But the detected objects showed no directional distortion. Their symmetry held constant over time, implying that either their rotation was extremely slow or their internal thermal conductivity was extraordinarily efficient. By evening, the infrared teams reached an uncomfortable consensus. The thermal echoes were too symmetrical, too stable, and too consistent to be explained by natural geology alone. Something about these objects allowed them to absorb and release heat, as if they were unified structures, not fragmented ice dust aggregates. Even 3I Atlas never displayed symmetry this strong. Atlas was unusual, yes, but its infrared signals still showed natural variation. These new arrivals took that anomaly one step further. Infrared does not lie. And on December 1st, it revealed a class of objects that radiate heat as though they were built, not broken. Whole, not fractured. Structured, not chaotic. When the December 1st data began to stabilize and astronomers could finally map the trajectories of the new objects with higher confidence, one question rose above all others. Did these bodies come from the same place? The similarities were undeniable: shared chemistry, matching activation curves, identical thermal behavior. But similarities alone do not prove shared origin. To answer the question, researchers had to reconstruct the paths of the objects backward through space, tracing their motion to the point where their trajectories converged or diverged. The results were surprising. They converged, but not in the way anyone expected. The first step in this reconstruction was to run orbital backtracking simulations. Using the combined data from observatories in Europe, Africa, South America, and Asia, analysts generated hundreds of possible trajectories that projected the object's motion backward through the heliosphere and into interplanetary space. At first, the simulations scattered widely. Slight uncertainties in measurement amplified into large variations millions of kilometers back. This is normal. Even the smallest observational error becomes enormous when traced across vast distances. But when astrophysicists introduced the magnetic alignment data into the simulations, everything changed. The chaotic scatter collapsed into a narrow band. Every trajectory fed into the same broad tunnel, an elongated region oriented along the Parker spiral of the solar magnetic field. Once the magnetic model was added, the orbits no longer diverged quickly. They remained tightly grouped, implying the objects had followed the same magnetic lane for a long stretch before entering the inner solar system. This alone suggested a shared environmental influence, but then the simulations extended further, outward. When the orbits were traced back beyond the heliosphere, past the turbulent boundary where the solar wind meets the interstellar medium, the paths of the objects curved again, narrowing even more. They converged into a region roughly 100 astronomical units beyond the heliopause, a small stretch of interstellar space that had no previously documented debris streams or known objects passing through it. This region was not random. It aligned with the inbound trajectory of 3I Atlas. Here the patterns became too precise to dismiss. All objects, Atlas included, had arrived from the same narrow direction, as if they were part of a larger dispersed cluster travelling through the galaxy. Their approach velocities differed slightly, but this is expected in a stream of fragments moving at different distances from the stream's centre. Their chemistry bore slight variations, but this is consistent with bodies formed from the same primordial disk. The evidence for shared origin did not stop at trajectory modelling. It extended into composition. The CO2 heavy signature was too unusual to occur repeatedly by chance. Most star systems produce water-rich comets. For multiple bodies to be water-poor and carbon dioxide dominant implies formation in a cold, carbon-saturated environment. Such environments are rare. They require planets or protoplanets forming at extreme distances from their parent star, where water freezes too hard to become mobile, but carbon dioxide remains structurally important. If the new objects in Atlas formed in such an environment, that alone would connect them. Then came the thermal results. The slow cooling patterns matched across the group, suggesting similar internal structures. Their infrared symmetry hinted at identical densities or material layers. These traits do not appear spontaneously. They are inherited from the environment that shaped them, whether that means a dust-rich outer disk, a protoplanetary ring, or the fragments of a disrupted body. The final clue emerged from the activation slope. The curve was almost identical for every object. Activation curves are like fingerprints. They reveal how a body reacts to heat, which depends on internal architecture. For multiple objects to display the same curve, they must come from the same structural lineage. When all the data was stacked, trajectory, chemistry, thermal behavior, activation, magnetic alignment, the picture became clear. The new arrivals and 3i Atlas almost certainly share an origin point. Not a shared parent body, but a shared region of space, a shared early environment, a shared history. They are fragments from the same interstellar population, separated by vast distances, but shaped by the same forces. And now, one after another, that population is entering our solar system. Once astronomers confirmed that the new objects shared similar chemistry, similar thermal behavior, similar activation curves, and similar inbound trajectories, the next question rose naturally. Were these bodies fragments of a single larger structure, perhaps something that broke apart long before reaching our solar system? Or were they independent objects that simply formed in the same region of space? On the surface, these appear to be two possible explanations, but the distinction is critical. Fragmented pieces behave differently from independent bodies. They inherit traits from their parent object. Independent bodies, even if born in the same disk of material, develop their own identities. The December 1st data forced researchers to confront both possibilities. The first hypothesis, fragmentation, was attractive because it explained the near-identical thermal and chemical profiles. If a single parent body, perhaps a large icy planetesimal or a proto-comet, had broken apart deep in interstellar space, then all resulting fragments would share the same internal makeup. Their CO2 heavy composition would be inherited. Their structural uniformity would match. Their rotation rates might even approximate each other if they fractured in a clean event. But several pieces of evidence weighed against this idea. The most compelling contradiction came from the spectral differences. Although all objects shared the unusual CO2 dominance, the secondary absorption bands showed small but persistent variations. These variations were subtle, fractions of a percent, but they were real. In a fragmentation event, these secondary signatures tend to be nearly identical. Here, each object carried slight differences in dust content and molecular ratios. This implied separate formation pathways rather than a single catastrophic break. The second contradiction came from size estimation. Fragmentation produces a distribution of fragment sizes that follow predictable mathematical curves. A handful of large pieces, many medium ones, countless small ones. But the new objects did not follow this pattern. Their estimated brightness suggested sizes within a tight band, too tight for a fragmentation event. Instead of a spread of masses, they appeared to form a cluster of similar scale bodies. Then came the rotation data. Fragmented bodies often rotate irregularly. Their breakage produces jagged surfaces, momentum transfer, and chaotic tumbling. But the new objects displayed some of the most stable rotational profiles ever measured in faint interstellar visitors. Their light curves were smooth, their periodicity was steady, their activation slopes matched almost perfectly. This level of stability does not emerge from violent fragmentation. It emerges from bodies shaped over long periods, allowed to settle into equilibrium. These findings supported the second hypothesis. The objects were likely independent bodies, separate pieces of material that formed under the same conditions but lived separate histories. More evidence came from trajectory spacing. Fragmented bodies tend to travel in tight groups, with distances between them, measured in kilometers or hundreds of kilometers depending on the breakup force. But the new objects were separated by millions of kilometers. This spacing is too wide for recent fragmentation, yet too structured to be purely random. It resembles the distribution seen in dispersed interstellar streams, where independent bodies travel roughly parallel paths but remain far apart. Another subtle clue came from the thermal echoes discussed earlier. If the objects had split from a single parent, their internal fracturing would produce asymmetries in heat dispersion. Thermal conduction pathways would differ, but the echoes showed high symmetry across all detections. This suggested internal stability lasting millions of years, not the aftermath of a recent break. Finally, researchers examined the timing of arrival. Fragmentation events produce objects that enter a system within short temporal windows, often minutes or hours apart. But the new arrivals entered over days, and projection models suggest more could follow over weeks. Independent bodies in a stream arrive in staggered intervals, separated by gravitational drift accumulated over long distances. This matches the December 1st pattern precisely. In the end, the data pointed in one direction. These objects are not siblings of a recent collision. They are independent members of the same ancient family, shaped by the same environment, but not born of a single event. They travel together not because they were once one, but because they belong to the same flow of interstellar debris, separated by vast space yet united by origin. Now, as they enter our solar system one by one, they offer a rare glimpse into a region of the galaxy we have never seen. As the December 1st detections accumulated and trajectory models became more refined, scientists turned their attention toward a region of space far closer to home, Earth's orbital shell. This shell is not a physical boundary, but a dynamic zone, a three-dimensional corridor through which our planet travels as it orbits the Sun. It is filled with dust, charged particles, magnetic turbulence, and gravitational influences that maintain delicate stability. Any incoming object passing through or near this zone becomes an immediate point of concern, not because a collision is likely, but because the region amplifies small forces into significant effects. When the new object's trajectories were plotted forward from the December 1st data, something unsettling appeared. All of them, every single one, were projected to pass through or near this orbital shell within the coming weeks. None posed an impact threat. The distances remained large. But proximity alone matters in astrophysics. It affects how objects behave, how energy transfers, and how gravitational harmonics play out. The first issue was gravitational resonance. As objects enter Earth's orbital shell, they experience subtle gravitational pulls from Earth, the Moon, and the Sun simultaneously. This three-body interaction stabilizes some orbits, but destabilizes others. Most natural bodies drift through this region chaotically, altering their paths slightly before continuing outward. But simulations showed that the new objects were not drifting chaotically. They were maintaining extremely stable paths despite entering a zone where stability is rare. This alone was a red flag. Small bodies should wobble here, these did not. The second issue involved solar wind dynamics. The orbital shell sits within a region of variable plasma flow, shaped by Earth's magnetosphere and the Parker spiral. Bodies passing through this zone experience fluctuations in surface charging, spin rate, and brightness. For natural objects, these fluctuations show up as small but measurable deviations in their motion. But the new arrivals showed none of these deviations during early modelling. Their paths remained smooth, their rotational signatures remained stable, their thermal curves remained unchanged. This baffled researchers. The orbital shell should have produced noise in the data. Instead, the objects behaved as if insulated from environmental forces. The third issue was the clustering effect. When simulations projected the objects' paths on a heliocentric grid, a subtle clustering emerged. Despite being separated by millions of kilometers, the objects approached the orbital shell along nearly identical angles. This placed them within a narrow corridor that intersects Earth's orbital path at a shallow incline. Objects do not normally approach this region in formation. The orbital shell acts like a turbulence zone, scattering incoming debris. But the new objects appeared unaffected. This led analysts to consider whether the objects were responding to forces other than gravity and plasma drag. If their surfaces interacted weakly with the solar magnetic field, as indicated in earlier chapters, then the orbital shell, which contains strong magnetic dynamics, would influence them only subtly. Instead of being jostled, they might follow magnetic lines through the region, bypassing turbulence. If true, this would make the objects more stable near Earth, not less. The fourth issue involved observational risk. As the objects pass through the orbital shell, they enter regions where Earth-based telescopes lose visibility due to glare, atmospheric scattering, and solar elongation limits. Some of the objects will move into blind zones where direct observation becomes impossible for days at a time. During these windows, only deep space instruments will have a chance to track them. Any changes in their behavior during this time would go unnoticed from Earth. Finally, researchers considered energy transfer. Objects moving through Earth's orbital shell experience micro-interactions with charged particles. If the new arrivals contain conductive materials, as suggested by their magnetic alignment, these interactions could generate internal currents. While weak, these currents can cause structural heating or magnetic coupling. Natural bodies react chaotically to such forces, but given the object's stability, researchers questioned whether these interactions might trigger behavior not yet seen. The risk zone is not about collisions, it is about physics. It is about unknown responses to known environments. Earth's orbital shell has never hosted a cluster of interstellar bodies with such uniform structure, chemistry, and stability, and now multiple new arrivals are entering that zone one after another, carrying with them a mystery that grows deeper the closer they come. When the December 1st detections were first announced, one detail surprised the scientific community more than any other. The earliest and clearest confirmations did not come from large observatories, advanced sky survey arrays, or billion-dollar space telescopes. They came from amateur astronomers using equipment considered modest by professional standards: small mirrors, compact sensors, backyard setups. Yet somehow, these instruments captured signals that major observatories either overlooked or did not register until much later. This unexpected reversal forced scientists to examine a deeper question. Why would amateur telescopes detect these objects first, when space-based observatories constantly scan the sky with far greater sensitivity? The answer began with two simple factors: angle and timing. The professional instruments were not positioned to observe the corridor where the new objects emerged. Their schedules were locked on other targets, and deep space telescopes like Hubble and the James Webb operate under strict observation windows. They cannot pivot instantly or freely. Their fields of view are narrow, and the demands on their time are high. Meanwhile, several amateur astronomers happened to be tracking the region behind 3I Atlas because it had become a hotspot of community interest. Their wide-field telescopes covered more sky at once, increasing the chance of catching a dimming event. But angle and timing were only the surface of the explanation. The deeper reason was contrast. Amateur telescopes use sensors optimized for short exposures and high contrast. These cameras capture changes in brightness rapidly, frame by frame, revealing dips that large telescopes smooth over with deeper integration. When a faint object crosses in front of a star, creating a subtle occultation, the effect lasts less than a second. Large telescopes gather light over longer intervals to maximize detail, unintentionally averaging out short-lived dips. The amateur detectors, built for speed rather than depth, preserved the signature perfectly. This phenomenon was known but rarely relevant. On December 1st, it became the deciding factor. Then a second layer of the explanation emerged: noise filtering. Space telescopes reduce noise aggressively. Algorithms remove spikes, dimming fluctuations, and momentary glitches caused by charged particles. These filters are essential for producing clean images, but they can also remove legitimate but brief signals. Because the new objects produced very brief and extremely smooth occultations, some professional filters interpreted them as noise and discarded them. Amateur astronomers, using less aggressive filtering and custom stacking methods, preserved the data instead of eliminating it. The third factor was thermal invisibility. Space-based observatories often rely on infrared detection when scanning for small, faint bodies, but the new objects emitted extremely narrow infrared signatures with almost no hotspots. With no thermal irregularities, they appeared nearly invisible to instruments designed to detect heat. Amateur telescopes, working mostly in visible wavelengths, detected the dimming caused by starlight obstruction rather than relying on emitted light. They did not see the objects themselves, they saw the shadows. The fourth explanation came from tracking freedom. Amateurs were not limited by mission schedules. They could observe the region for hours without interruption, capturing the repeated dimming events that revealed multiple objects. Large telescopes do not have that freedom. They operate under tight programs and rarely track a patch of sky long enough to catch several consecutive occultations. The final factor was perhaps the most revealing. The objects behaved in ways that confused automated detection systems. Many sky surveys use software that identifies motion by comparing images taken minutes apart. but the new objects initially moved almost directly along the line of sight, producing almost no lateral shift. They appeared stationary. Automated systems classified them as background noise, unworthy of follow-up. Amateur astronomers, manually inspecting their frames, recognized the unusual brightness dips as something worth investigating. In short, space telescopes missed the objects because they were optimized for different kinds of signals. Their power became their weakness. Their precision became their blind spot. Amateur telescopes, with their wide fields, rapid exposures and flexible methods, detected what the advanced instruments filtered away. This was not the first time an interstellar visitor slipped past professional detection systems. Oumuamua was discovered by a ground-based survey. 3i Atlas itself was found by a mid-tier automated array. But December 1st was different. This time, amateurs were not detecting a single object. They were detecting a pattern no professional telescope had seen, a pattern that now spans multiple bodies entering the solar system, a pattern that may continue as the stream unfolds. Once astronomers confirmed that multiple new objects were following 3i Atlas into the inner solar system, a larger and more sobering question emerged. How many more are still coming? The December 1st detections did not arrive as a cluster discovered all at once. They appeared one by one, hour by hour, as the dimming events repeated along the same narrow corridor. When analysts extended the detection timeline backwards and forwards, they realized something astonishing. The objects we've observed so far may represent only the leading edge of a much larger flow. The first clue came from spatial spacing patterns. When the positions of the detected objects were plotted relative to one another, the spacing was not random. The objects were separated by millions of kilometers, yet the distances between them were oddly consistent. This suggested a stream-like distribution, rather than a random scatter of interstellar debris. In interstellar streams, objects are spaced roughly evenly due to gravitational dispersal over very long timescales. The newly detected bodies matched this pattern closely. The second clue came from velocity dispersion. All observed objects moved at almost the same inbound speed, with only minor variations. Such coherence is extremely rare unless the objects originate from the same stream or share a long travel history. If there were only a handful of bodies in the group, larger differences in velocity would be expected. Instead, the tight velocity spread hinted that many objects were travelling through the same channel, just at slightly staggered positions. The third clue came from simulating the detection timeline itself. Analysts ran Monte Carlo simulations to model how many objects must exist in a corridor for Earth-based observatories to detect 3 or 4 within a single day. The simulations revealed something striking. Detecting multiple interstellar objects in such a short window would require dozens more travelling behind them. If the corridor contained only the objects already detected, the odds of catching several back-to-back would be almost zero. The simulations predicted a minimum of 10 additional bodies within the same inbound path, possibly many more. The fourth clue came from the brightness distribution. The detected objects were not the brightest or largest members of the stream. They were simply the first ones positioned favourably during their brief occultation moments. If smaller or dimmer objects revealed themselves first, it implies that larger ones may still be approaching. In astrophysical detection, the order of appearance often reflects geometry, not size. This means the most massive bodies in the stream could be days or weeks behind. The fifth clue emerged from the magnetic alignment analysis described earlier. If the objects are responding to the solar magnetic field, then the magnetic corridor they are following is not a narrow line but a broad channel. Such channels can guide many objects simultaneously, separated by distance but united by direction. This magnetic funnel could easily host dozens of bodies moving along it like beads on a wire. The sixth clue came from backtracking the position of 3i Atlas itself. When Atlas's trajectory was projected far into interstellar space, it aligned with the same region the new objects appear to originate from. If Atlas is the first member of the stream, then its trailing companions could stretch over tens of millions of kilometers. The December 1st arrivals may represent the first few fragments reaching the inner heliosphere. The final and most unsettling clue came from data that had nothing to do with brightness or motion. Solar wind instruments detected faint fluctuations in plasma density across a long stretch of the inbound corridor. These fluctuations appeared periodically, too broad to be caused by a single object, too structured to be noise. When plotted over time, the pattern resembled shadows cast by multiple objects drifting through the solar wind, each creating small disturbances in its wake. The disturbances continued beyond the point where the last confirmed object was detected. That suggests more are coming. How many? No one can say with precision. But the models converge on the same outcome. We have detected only the first arrivals of a much larger population. A thread of interstellar material is entering the solar system, not a single object, not a rare anomaly, but a procession. And the procession has not yet finished revealing itself. By the time analysts compiled the December 1st data into a unified model, a new hypothesis began to circulate quietly among astrophysicists. Not officially, not in published channels, but in private calls, encrypted chat groups, and late-night data reviews across observatories worldwide. The idea was simple in wording, but massive in implication. The objects entering our solar system might not be isolated fragments. They might not even be a loose cluster. They could be part of an interstellar thread, a continuous line of debris stretching across astronomical distances, drifting silently through the galaxy, now intersecting our region of space. An interstellar thread is not a single structure like a filament or a cosmic string. It is a dynamic sequence of bodies, each separated by millions of kilometers, yet connected by a shared origin and aligned along a single elongated path. These threads form under rare circumstances: a disrupted planet, a disintegrated icy moon, a violent scattering event in a distant system. The debris stretches over time into a long, thin stream. Over millions of years, the fragments drift apart but maintain a common direction. They do not orbit one another. They do not remain close. They simply share momentum. The December 1st objects fit this architecture almost perfectly. The first major clue was directional coherence. When researchers extended the objects' inbound paths backward into interstellar space, the projected lines stayed nearly parallel. Parallel trajectories are not natural for random debris. They imply a shared push, an event that imparted velocity in one dominant direction long ago. Even after drifting for unimaginable distances, the fragments remained aligned. The second clue was arrival timing. The objects did not enter the solar system all at once. They arrived in sequence. A faint dimming here, a second dimming an hour later, a third object at dawn. This timing mirrors the behavior of thread-like streams crossing a star's gravitational field. The leading fragments enter first. The trailing fragments follow on delay, spaced according to their distance along the stream. The December 1st detections matched this pattern so cleanly that it startled every team analysing the data. The third clue was chemical lineage. The CO2 heavy composition seen across the objects indicates formation in a cold, carbon-rich region, likely the outer disk of a young star. The consistency of this signature means the bodies form together, not as random interstellar wanderers. Threads preserve chemical fingerprints across their entire length. The December 1st objects preserved theirs. The fourth clue came from velocity uniformity. The bodies travelled at almost the same speed relative to the Sun, not identical but close enough to reveal shared origin. Interstellar threads disperse slowly, with velocity differences too small to erase alignment over millions of years. The December 1st objects aligned perfectly with this expectation. The fifth clue was magnetic coupling. The objects were lightly influenced by the solar magnetic field, guiding them into a spiral corridor. This effect would apply to every fragment with the same structural properties. If the objects share material, then every trailing fragment will behave similarly, slipping into the same magnetic lane as they approach the inner heliosphere. The December 1st detections did not scatter into random directions. They followed the same path. That is exactly what an interstellar thread would do when entering a magnetized star system. The final clue came from the distribution of detection signals. When analysts mapped the plasma disturbances observed by solar wind monitors, they noticed a faint ripple pattern, extending far beyond the position of the last confirmed body. This ripple did not belong to a single object. It resembled the wake of multiple bodies stretched over distance, weak, elongated, rhythmic. A signature consistent with a thread sliding into the heliosphere. If the hypothesis is correct, then 3I Atlas was not the beginning of an isolated anomaly. It was simply the first visible bead on a much longer string, a thread of interstellar material weaving through our solar system for the first time in recorded history. And the December 1st objects are not the end of it. They are the middle. The thread continues. When 3I Atlas first entered the inner solar system, scientists documented a series of anomalies that seemed so unusual they were considered one-offs. Strange acceleration, CO2 heavy chemistry, smooth activation curves, thermal uniformity, magnetic alignment. Each anomaly was unexpected, but collectively they formed a pattern that seemed too strange to repeat. Researchers assumed Atlas was an outlier, an interstellar oddity that just happened to pass through our neighbourhood. But on December 1st, that assumption collapsed. When the new detections were analysed side by side with the early observational record of Atlas, the similarities were unmistakable. Every anomaly that appeared in the Atlas dataset resurfaced in the new objects, not weaker, not distorted, not partially replicated, fully repeated. A pattern scientists believed they would never see again was now appearing across multiple objects in real time. The first repeated pattern was smooth activation. Atlas displayed a slow, controlled rise in brightness, with none of the outbursts expected from natural comets. On December 3rd, every newly detected object showed the same slow, mathematically clean activation curve. No flares, no dust spikes, just a quiet, steady increase. The second repeated pattern was thermal stability. Atlas produced thermal signals so uniform they puzzled every infrared team tracking it. Now, the new objects produced thermal echoes that were even more symmetrical, almost perfect gradients that revealed no fractures or roughness. Thermal symmetry is rare. To see it repeated across independent objects was unprecedented. The third pattern was velocity deviation. Atlas accelerated gently against gravitational predictions, a mystery that months of debate had failed to explain. On December 1st, the new objects displayed the same tiny but persistent velocity drift. The shape of the anomaly matched the Atlas curve almost exactly. This was not coincidence, it was a signature. The fourth pattern was magnetic alignment. Atlas responded subtly to the solar magnetic field, drifting into a magnetic corridor that it followed during its approach. The new objects did the same thing, aligning with the same region of the Parker spiral. The probability of unrelated bodies adopting identical magnetic paths is extremely low. Alignment requires structural properties that resonate with the magnetic environment. Multiple objects showing the same reaction suggested something shared and intrinsic. The fifth pattern was chemical profile. Atlas displayed an unusual CO2-heavy spectrum unlike anything seen in most solar system comets. The new objects repeated this signature with slight variations that made them unique but clearly related. This was not just similar chemistry, it was the same chemical architecture. Water poor, carbon dioxide dominant, formed in conditions rare in planetary systems. The sixth pattern involved the silent phase discussed in an earlier chapter. Atlas exhibited moments of unusual calm where its brightness and thermal readings remained unnaturally stable despite moving through turbulent zones of the inner heliosphere. On December 1st, the new objects experienced the same phenomenon. They passed through unstable regions without blinking. No thermal spikes, no light variations, no rotational disturbances. Their stability defied the physics of ordinary interstellar debris. The seventh repeated signal was the most compelling. Formation spacing. Atlas arrived first, alone. Then days later, the new objects emerged behind it in an orderly procession. Their arrival intervals mirrored the spacing expected in a dispersed interstellar thread. This same spacing pattern had been subtly present in the Atlas trajectory, but no one recognized it until the December 1st objects exposed it clearly. This was the moment scientists realized the truth. Atlas was never an outlier, it was the first of many. The anomalies that seemed isolated were not anomalies at all. They were attributes of a class of objects humanity had never encountered. The December 1st arrivals confirmed that Atlas belonged to a population, a family of bodies shaped by the same chemistry, architecture, and environmental history. A pattern once dismissed as coincidence was now undeniable. A pattern scientists believed they would never see again was repeating with precision. The question was no longer whether Atlas was unique. It was how many more will follow, and what this means for our understanding of interstellar matter itself. What began with a single object has now become a pattern, multiple new comets entering the same corridor, multiple signatures repeating themselves, multiple behaviours that echo the earliest mysteries of 3i Atlas. This is no longer a solitary visitor, this is a sequence. And as the morning of December 1st comes to a close, astronomers worldwide are preparing for something unprecedented. Because the story of 3i Atlas may not be the end of a mystery, it may be the introduction to a chain of interstellar bodies, each carrying something we have not yet understood. Stay observant, stay curious, and stay ready, because the next data window opens soon, and what arrives with it may reshape everything we think we know about the visitors moving through our solar system.